All right, so very happy to introduce Yaping Yang from the University of Melbourne, who will tell us about perverse coherent sheaves on toric, Calabi-Yau threefolds, and cohomological Hall algebras.
Thank you, Odette. So I would like to thank the organizers for inviting me. It's my great pleasure to speak in the conference. So this talk is based on my joint work with Mira Rapcak, Yang Soibelman, and Zhao. Okay, so let me start. So I want to start the motivation of my talk. So for the setup, I'm taking X to be a local toric Calabi-Yau threefold. Local toric Calabi-Yau threefold. And here, so by local, I mean it's an open neighborhood in a compact Calabi-Yau. Open neighborhood. So in particular, X itself is not compact. And I assume there's a resolution singularity. I call it F, so Y. So this is a resolution of singularities. And here Y is affine. Okay, and also assume the dimension of the fiber. Dimension of the fiber of F is less or equal to 1. So now let me give you a few examples of this setup. So example, so one can take X to be C cube. This is smooth. And so I'm taking Y to be C cube as well. So the function F is just the identity. And I will use a physicist's way of representing this X by drawing the toric diagram. Okay, so the toric diagram for C cube is this. And here, so all the faces are the toric divisors. So I have C2, XY, C2, YZ, and C2, XZ. All right. And another example, so I can take X to be the resolved conifold. So X is the total space on P1 of O negative 1 plus O negative 1. And so this is the resolution of the conifold XY equal to ZW in C4. So this is my resolution of singularity F. And if I draw the toric diagram for this case, so I have this. All right. And now also that's my base space X. So now I want to fix a sheaf. So this is some preferred sheaf on X. So for example, you can take V to be the structure sheaf on X. Okay, so I want to consider the modular space of certain framed stable sheaves on X. So I will denote that thing by M. So I will consider M to be the following moduli. So moduli of pairs F, S, where so this F is a perverse coherent sheaf. And so I will use a notation F lies in perverse of X / Y. So this category of perverse coherent sheaves is a abelian category in the derived category of coherent sheaves on X. And so the element here will be a complex of coherent sheaves. And so this perversity is given by this function F, this resolution of singularity. And so the S, so this is the framing. So it's a morphism, homomorphism from the function, from the sheaf V to F. This is the homomorphism. And this modular space also have some stability conditions. Just write stability. Okay, so this is the type of modular space I'm considering because this is a local picture. So always this modular space is some critical locus of a global function F.
Yaping, can I just ask what So what is Calabi-Yau, X or Y?
So Calabi-Yau is the condition C1 of the tangent is trivial.
But where are you imposing that condition, on X or on Y?
Oh, on X.
Uh-huh.
Yeah.
And perverse means something like that it has no skyscraper sub-sheaves along the exceptional divisor or something?
Oh, I can write down the perverse coherent explicitly here. So the perverse coherent, so some perverse coherent sheaf just means if I look at the cohomology, so if and only if the cohomology of f equal to 0, so this is concentrated on degree 0 and -1. If I is not equal to 0 and -1, and also if I look at the push forward one f lower star of h0 equal to trivial, and so at 0, the push forward of h -1 equal to trivial. And also, if I look at the homes, so home from the h0 to c is always 0 for any c on x, such that the push forward of c equal to 0. So that's the condition for perverse coherent sheaves. Right. So let me give you some examples of this for this modular space. So for example, if I take x to be c cubed, so this category of perverse coherent sheaves is just the coherent sheaves on x. And for example, if I'm taking my v to be the structure sheaf, and one example for this moduli will be the Hilbert scheme of points on C cube. So this is a moduli parameterizing all the ideals in a polynomial ring with 3 variables of finite length. And so there's a torus action if I look at the torus fixed points. So this will consist of all the monomial ideals. So this consists of the 3D partitions. I'll give you a picture. So this is the torus fixed points for this example. And also if I take my V to be, if I'm fix a divisor to be C2, so I have 3 toric divisors in this example. So I'm fixing one of them in X. If I look at the structure sheaf on this C2, and my moduli, as an example, could be the Hilbert scheme points on C2. Okay, so this is the moduli of ideals in a polynomial ring with 2 variables and the torus fixed points. So this is all the monomial ideals of 2 variables. So this is all the partitions of all the partitions. Okay, so that's a second example. So as another example, if I'm taking X to be the resolved conifold, so this is the O -1 plus O -1. Okay, so let me describe for you what's the perverse coherent sheaves on X. Right, so for this example, there exists a tilting vector bundle. And so it's just, so I denote this thing by P. So it's OX plus the push forward. So if I denote the map to P1 by pi, so the pullback of O1. So that's a tilting vector bundle. And so the category of perverse coherent sheaves as an abelian category is isomorphic to the modules over the endomorphism of P. Okay, right. So this algebra can be made very explicit. So this is just the Jacobian algebra of some quiver with potential. Q and W. So this is the quiver. This is the potential. Right. So the Jacobian algebra means I'm taking the path algebra of the quiver by imposing some relations, and those relations are obtained by the derivative of my potential. Okay, and so let me draw the quiver for you in this example. So the quiver is this one. So I have 2 vertices and 4 arrows in between. A1, A2, B1, B2. And the potential in this example is A1, B1, A2, B2, minus A1, B2, A2, B1. Okay. Right, so that's the perverse coherent sheaf. And so if I fix this sheaf V to be the structure sheaf on the whole thing, so my modular space, so this modular space depends on a stability condition. I will write the stability condition by zeta. So this depends on the stability condition zeta. In this case, zeta is a pair of real numbers. Okay. And so the modular space, in this case, is started by Nagao-Nakajima. Right, so they determine the chamber structure for the for this modular space. So let me draw you the picture. I have it here. This one. Yeah. Right, so this is a picture for the chamber structure for the modular space M. And so if you see the walls, so there are infinitely many walls, yeah? So those walls are the locus where my modular space is singular. And inside the wall, so those modular spaces are smooth. So the semi-stable points and the stable points coincide. And also, so the modular space inside the chamber, it's only dependent on the chamber. Okay. And so this wall coincides with the root hyperplanes. Of affine SO2 hat. Right, so in particular, so if I look at this wall, right, so if I look at this off diagonal, right, so this word corresponds to the imaginary root hyperplane. So imaginary. And all the other words are the real roots hyperplane. So all the others correspond to the real roots. All right. Right. So right. So so there are infinitely many real roots, and right. So if you see here, so the roots getting closer to the imaginary root, but can never equal. And also here, so the real roots getting closer and closer to the imaginary root and can never equal. And in the limit case, right, so the limit, so under this imaginary root hyperplane, so in the limit case, this is the dt modular space. So this should be dt for x. And so above the root hyperplanes, this imaginary root hyperplane, the limit case, so this recovers the pt. So this is the pt for the resolved conifold, pt for x. And right, so on top of this, so this is the dtpt for the x for the for the resolved conifold, and under this is the flop of x. So this should be x plus, which means the flop, x plus dt for x plus.
Yeah, Yaping, what does dt mean? Oh,
so the dt is just so the ideal sheaves. So it's a modular space parameterizing the ideal sheaves for the dimension 1 subscheme in this case. And PT is a modular space parameterizing the stable pairs. Right. And oh, there are some questions in the chat. Oh yeah, thank you. And so there's also there's this block. So this is a non-commutative DT, so the NCDT. Right. So if you like a quiver, let me see. Right. So if you like a quiver description, I can also draw the quiver for those moduli. So this block. So this has a quiver description. Right. So, so it's the following. So I have the quiver for the perverse coherent sheaves. And so this is a frame in the case. So I'm adding a framing like this. Okay. And so that's the quiver description for this chamber. And if you want to get in quiver description for other chambers, so you can do a quiver mutation. So if you do a mutation, you'll get quiver for other chambers. Okay. Okay.
Sorry, so Yaping, could I ask
Yeah.
a question?
Mm-hmm.
So for this, so this quiver that you've written down is, this is just telling me what the category of perverse coherent sheaves are.
Yes.
And then am I right in thinking that all of these different moduli spaces are still moduli spaces of objects in that abelian category, but with different stability conditions? Or is there some?
It's a way of framing. So the perverse coherent sheaves see this quiver without the framing. And those modular spaces that have this framing together with the stability condition. So for example, this NCDT, so it's a representation of this quiver and whose stability condition is a cyclic stability condition. Yeah.
And so the other chambers, are they the same quiver plus framing, but with different stability conditions? Or
so there are two descriptions using quiver. So you could use this quiver by imposing some different stability condition. It's not cyclic stability. Or if you do this mutation quiver, you'll get a different quiver, but with stability condition.
Okay, so you've just described, so you can do this mutation and describe this abelian category in terms of a different quiver, and then the stability condition is
exactly.
I see.
That's right.
Okay, thanks.
That's right. Okay. Right. So I do this mutation. I can get the quiver description for different chambers for the modular space. Okay. So now let me give you some next picture. So so if I can draw the torus fixed points for the stability for the modular space is on the PT side. So if I look at the torus fixed points, this also have a nice picture. So this is parameterized all the finite type parameter partitions. This one. All right, so so this picture, so if you see the black stones, so so that's the basis. So so the black stones will be the basis of so one of the vertex. So let me see. So if this is V1, this is V2. So the basis of V1, and if I see the white stones. So this is the basis of V2. And so all those maps in between, so I have A1, A2, B1, B2. So you can see it using so this is the map from black to white, from V1 to V2. So I have A1, A2, B1, B2. Right, so there are also some nice pictures describing the torus fixed points of the PT. Okay, right. So for me, I'm interested in the cohomology of this modular space and with coefficient in some perverse sheaf. So this is the perverse sheaf of vanishing cycle of F. Okay, so so all those pictures will be, so by localization, all those pictures will describe a basis for this vector space. And so I'm interested in the combinatoric and computation for the cohomology. Torics and computations. Okay. Right, so before we have this abelian category perverse coherent sheaves on X. And for this, by choosing a tilting object, and I can get a quiver and potential for this abelian category. And for a quiver with potential, so one can define the Cohomological Hall algebra, so COHA of Kontsevich and Soibelman. So I'll just denote this thing by COHA of X. Okay, so this is defined by Kontsevich and Soibelman, associated with the quiver and potential. And the general conjecture we propose, so conjecture. So first of all, this COHA, so this is not algebra. So COHA of X on the cohomology of the modular space. And so this action is as raising operators. So in other words, if I see those partitions, the boxes, this is the adding boxes. By adding. Okay, so so this moduli, so this action is for any sheaf V and for any stability condition zeta. Okay, and so this COHA action only sees the raising operators, and in order to study the representation theory, we also need the lowering operators. So conjecture 2, so the dream field double of the COHA. Also X, so X on the cohomology by adding the lowering operators. So we see the operations by removing the boxes. And also, so this dream field double can be made very explicit. So, so this thing factors rules. Some shifting the Yangian. Okay, so I will explain this shifting later. So the combinatorics for in this example, for example, I have all the partitions, all the 3D partitions. And those COHA will see the combinatorics, like how you're adding boxes, how you're removing boxes. Right, so also the character for this modular space. So in this example, it's the McMahon function. So this thing is like a vector space, right? So whose Euler characteristic, whose character gives you the McMahon function. So all those invariants, I think people care. So like in this picture, so I have the dt of the PTs. It's a two different modular space, and there's a word crossing. Like if you want to compare the dt invariant, want to compare the PT invariant, so you can never cross this wall. But this thing gives you a way of comparing dt and PT in this picture. Yeah, this modular space certainly is interesting, and like how to compute, how to find the symmetries for those modular space sounds interesting to me. Right, and COHA and those shifted Yanking is just a way of putting those invariants, do the computations together. So
when you say shifted Yangian, what's the Lie algebra?
So what's it? Yeah, I'll describe the Lie algebra in this general. So I will describe the root system for you later.
Okay.
Yeah. Right. Yeah. So so maybe I'll just roughly say part 3. So in some special cases, the action in 2. So this thing leads to other interesting structures. So for example, if I'm taking my sheaf to be some functions on the effective divisor in X, the divisor. And so for this, we can get a VOA structure, the vertex operator structure on the cohomology of the modular space. So this is the famous AGT correspondence from physics. Yeah, for our next question, so let me describe the shifted Yangian, or at least tell you what's the root system and how do I see the shifting for this general Calabi-Yau.
Can I ask, is that VOA, is that just COHA or the double of the COHA?
So so only for the double of COHA, you can see the VOA. So if
Okay.
I look at the COHA, yeah, so like this, what is it called? The free field realization, it depends on the co-product for your Yangian or your double of COHA. Right, so only you have the 4 things, you can see the non-trivial co-product.
Great, thank you.
So let me say some words about the root system and the shifting Yangian. So in this perverse coherent sheaves, so if I look at the Gaussian group for this, so I can pick a set of simple objects. So I call it SI. So those are simple objects. So I can consider those as the simple roots. Okay. And for the Cardan matrix, so I'm computing the pairing between those simples. So the pairing of SI, and this is some X pairing. So I'm computing the X among those simples. So just write X pairing. So this gives me the root system. And for example, if I'm taking Y to be the following equation defined by the following equation, xy equal to z to the m, w to the n, inside the c to the 4. And in this case, so if I draw the toric diagram, this is the toric diagram for x. So there are m lines on the right and n lines on the left. And in this example, so the root system will be the affine GLN of super case m/n, the super type A mn affine. Okay. So this is the example. So in this example, this is the root system, right? And right, so the Yanking will be associated to a Lie algebra of this type in the example. Okay, maybe so I'll quickly just say geometrically, how do you get the shifting? So the shifting, so my modular space depends on 2 things. So one is this preferred sheaf V. And in all my examples, this V comes from an algebraic cycle. Right, so some multiplicity of X and some effective divisor, for example. Right, so I will consider this thing. Right, so this algebraic cycle, I will consider the element in this Barrymore homology of X. Okay, and my modular space also depends on stability condition, zeta. Right, so I have, right, so in this dB co of X, I will, for each stability, so I can get a heart, which is isomorphic to the perverse coherent sheaves. And I can pick a set of simple objects in here. Those are the simples. And it's shifting geometrically. Right, so the shifting is shifting all the roots. So geometry is just this pairing of, so I have a class in the Barama homology, and I have a class in the Gaussian group. So, so I can take in the homological chain character map to map it to the homology of my X. And I compare this class. So this is my class in the Barama homology. So I compare those two, it tells me the shifting. Right, so, so let me just give you a
Yaping, can I just ask about the simples?
Yes.
So all I know about perverse coherent sheaves is that Bridgeland used them to construct flops or something. That if we look at a moduli of perverse coherent sheaves on some resolution, then this has a beautiful moduli space and it's the flop or something, or the flip. I can never remember which one. And so in that particular case, the simples are skyscrapers, and so there's infinitely many of them. And so why in this case do you have finitely many simple objects?
Yeah, I have, in this case, I have finitely many.
And why is that?
You have finitely many equivariant ones. There are infinitely many in general, but because you only care about the things that you push forward or supported at origin, that makes the finiteness.
Okay, so I should think about these as like, roughly speaking, like skyscrapers on T fixed points or something like that.
There are skyscrapers when you push forward to Y, but on X, this could be structure shifts on the exceptional curves and with twisting and shiftings.
Okay, thank you.
Yeah, thank you. So yeah, I'm going to give you this example for right. I'm going to write you the simple objects which is supported on the P1, the exceptional divisor. Exactly. Thank you. So so like in here, so X equal to the resolved conifold, and if I'm looking at this stability condition, so so those are the words correspond to the real root. So I will write the coefficients as m minus 1. And so this is a word m plus 1 and m. So I'm inside this chamber, so I'll denote the stability condition by eta m. So in this case, the two simples, S0, S1, so it's just the OP1s by some shifting, like Gufang said. This m plus 1, shifting by -1. Right, so you can do the explicit commutation in this case. If I'm picking this preferred sheaf V to be the structure sheaf, then then this pairing, so this shifting and pair X. So let's pair it with the imaginary root, which is the chain character map of sum of the simples. Okay, so this will, if you do the commutation, so this will be X pair with a point, so that's 1. So in other words, the proposal says here I should see the +1 shift of the imaginary root. Right, so I give you a general conjecture in this general setup for toric Calabi-Yau threefold. So theorem. Right, so all those conjecture can be checked for the building blocks. So maybe I'll just write this one shifted Yangian of GO1 hat acts on this equivariant cohomology of this modular space. And I should say, right, so for X, that's
sorry, which example is this now?
Oh, this example is for X equal to the total space of O -1 plus O -1.
All right, great, thank you.
For the example. Right, so we checked the correct shifting Yangian did X here. Okay, Right. So so I remark. So there are some building blocks for X. For a general X. So it's the following three cases: X equal to C cube, whose toric diagram is this, or X equal to the resultant manifold we have seen. This one. And X is so the total space on P1 of O negative 2 plus O. Right. This one. Yeah, so those are three building blocks. And so all the conjecture can be checked for those building blocks. The conjecture is true. The building blocks. And so in general, we don't know how to do it. So hopefully there's a way of gluing those blocks to get the whole X.
So in what sense are these building blocks?
In what sense? So if I look at the toric diagram, so for example, this one, so it can be glued over P1 of all those blocks. Right, so like this thing can be glued using these two C cubes over this P1. Right, so I think I explained the part 2 of this conjecture. So this double will see some shifted yanking, and we know exactly which shifted yanking to look at. And so maybe I'll say some words about part 3 for the last 5 minutes. Part 3. I can see other structures. So this is really motivated by physics. So for example, right, so I'll just give the theorem. So I'm taking X to be C cube. I'm taking my effective divisor to be this thing. So I have N1, N2, N3. So this means I have the multiplicity N1 of this divisor plus N2, C2 plus N3, C2. Okay, and I'm looking at yeah. So the theorem is so this yanking of GL1 hat X on the cohomology of the modular space. So in this case, this is the moduli of spiked instanton. Defined by Nekrasov. Okay, and if you wanna, so this has a quiver descriptions. I have one vertex with 3 loops and 3 framings. And those framing carry the multiplicity N1, N2, N3. Okay. And right, so in this example, so this action factors through a VOA. So it factors through a VOA. So this VOA is the so-called VOA at the corner, and defined by Rapcak and Gayotto. Right, so maybe you're not familiar with this VOA. So let me give you some special cases. So special case. So if I'm taking N2, N3 to be 0, so this divisor will be supported on C2 only. So right, so those two are 0. So I will see a divisor C2. And in this example, if I'm taking my framing N1 to be 1, and so this theorem is an old theorem of Gronovsky, Nakajima, saying so the modular space will be the Hilbert scheme of points on C2. And so this VOA is the Heisenberg VOA. So it's the action of the Heisenberg VOA on this cohomology of Hilbert scheme points on C2. Okay. And so for N2 equal to N, I have those higher rank thing. So higher rank moduli of instantaneous. And this is the theorem of Schiffman and Vassaro. And also Molly-Kochenkopf. Right, so so the VOA is the W algebra of GLN hat. And so this action is the cohomology of, I have the moduli of instantaneous with higher rank. Okay, so now you can see, so our theorem is have the triality. So I have those three. Oops. Right, so I have those three toric divisors, and it also have a nice VOA action. Okay, so this gives a generalized AGT correspondence in this setting. All right, so now I think my time is up. So I told you the VOA, so I will just quickly show you a nice picture. So this is the case so-called the D2 brane, the D4 brane picture. And I will quickly show you a slide, which is the situation for the D2 branes. So now, if I consider the PT moduli with some fixed asymptotics, and I can consider the PT moduli space, whose torus fixed point is, so I have those boxes, I can fill in the boxes in these PTs. And so the theorem is, so this is still work in progress. The theorem is one sheaf is Yangian acting on this cohomology of the PT. And so for those people who are interested in theoretical algebra, so so this partition is a triple of partitions. So if you send two of those partitions to be trivial, I see one partition. So this recovers the Varma module for the theoretical algebra. And so now I have three different partitions. So this is some representation outside the category O. So I have the I have the triality for this algebra action, and the actions is the Kaldromos operators and so on. Thank you.
All right, let's all thank Yaping.